continuation of the Design of Experiments series. I hope by now you've at least looked at or have seen both of the prior videos in this series. The first one was a 3-factor, 2-level, base level design of experiment with 8 runs. That was with an output that was attribute based, or basically yes/no type data. The second one was a little bit more complicated, but again it was 3-factor, 2-level, 8-run for variable type data outcome, and the analysis behind the whole process to get to the output of that particular process. We're going to jump off the path just a little bit on this video. This video is going to be talking to the hypothesis theory. And the hypothesis theory was first introduced in 1938 by Dr. R.A. Fisher, and it has been around for some period of time now. One that if you study it and understand it, you'll find a lot of application to it in the design of experiments field. And I'll talk heavily to it in about 15 minutes into this thing, to this last phase, to the application of it to the design of experiments and the application of design of experiments process. But let's just understand what we're going to talk about is the diagram that we have behind us. And the diagram has been written up in several technical magazines, and it's basically the base level of the hypothesis theory. And we will come back and talk to that in a moment. And we'll get into this one in a whole lot more detail. But before we get into the details of what the hypothesis theory is trying to tell us and the theory behind it, there's a very, very good analogy that was developed in the 1980s by an article that was written in Quality Progress magazine that had the analogy of the hypothesis theory to our courtroom situation. So let's use the analogy of the courtroom to try to explain what we're trying to do and what we're going to try to cover in the hypothesis theory. So let's go to the other side. And so what do we have over here? Well, let's look at what the outcome would be of a typical trial in our United States court system. We have across the top of these 4 boxes here what the jury found. And let's go across what the jury found because it's very closely to the hypothesis theory. Number 1, we have one side over here. The jury found the person that was put on trial not guilty. The second box over here, that the person was put on trial was found guilty. Notice that there is no outcome from the trial that has the person found innocent. In the courtroom situation, and similar to in the design of experiments area or in the hypothesis theory, it is proof beyond reasonable doubt that you are driving towards in your experimental process. And we'll explain that more as we go through this process. But understand, we never found anybody innocent in the process. We found insufficient evidence to support guilt, or in that particular case, not guilty. So let's come over to the other side. The side over here has, and I'm going to use the generic word for it, he did it. And I'm going to do on the other side of the word, he did not do it. Could have been a she, something along those lines. But what actually happened, or what actually the person that was put on trial did. What I want to do is I want to talk to 2 error boxes and then go flip over to the other side and look at where those error boxes customary are on the hypothesis process. Let's take the he did it and go to not guilty and the intersection between those 2. So we put somebody on trial. That trial, if it was found the person not guilty, but in actuality that person actually did it. That particular courtroom outcome in the statistics world, we're going to call it a beta error. And it's also codenamed in many statistical books, in many analysis, as type 2 error. Let's go to the next box, the error box, and go down to he did not do it, but was found guilty. In that particular case, we're going to call that an alpha error or a type 1 error. If you ever have difficulties remembering which one was type 1 and type 2, alpha, beta, type 1, type 2. There's a third box I've got up here called the power box, and that's where he did it, and he was found guilty. And I'll come back and talk to that particular box in a minute. But let's first get into the two types of errors associated with the experimental process. And let's flip it back over to the other side. In the actual application of a typical experiment, we might have what we are going to call a baseline analysis, or a sub O, or what has historically been called the null hypothesis. The null hypothesis basically says is, okay, let's do our experiment on our existing process. Let's take our experiment on our process that has been running now for 3 months, 4 months, 6 months. We have a history on it, and let's say that the outcome from this process might be the yield coming out of it. And we're measuring the yield on a daily basis. And we plot that yield out, and the yield follows a typical normal distribution. We would call that our A sub O. And let's take an actual example. Let's say that we wanted to put a new product in there, or a new supplier came in and came up with a new product mix that we wanted to use for our outcome, but it's more expensive of a product mix. So consequently, what we want to do is we want to prove beyond reasonable doubt that that new material that we brought into the process is going to give us an improvement in the yield coming out of our process. So we take our process and we measure it over the 3-month period of time. And then we take it and we move it and we put the new process in. This now is called A sub A, or the alternative hypothesis. Basically what we want to do is we want to prove beyond reasonable doubt that when we put the new material in, that it actually improved the yield coming out of the process. So we take and we put the new process in and we run it for a period of time. That could be as little as 24 hours, that could be as much as 24 days. The determination of the process is really up to the designer of the particular process. And when we do that, we get an output that follows a normal distribution. And there's an overlap between our original analysis and our new output called our alternative analysis. Now there's two boxes. If we were going to turn around and say that there was a difference when we added that new material into the process, there's two errors associated with that. Go back to the prior board, or prior analysis. There was the alpha analysis, the alpha error, and there was the beta error. The alpha error was the error that commonly associated on the courtroom was when we put somebody on trial and they actually didn't do it and they were found, we found them guilty. In the experimental world, very close analogy to that is the red zone over here. Notice the red zone in this particular diagram up here is all underneath our A sub O, or null hypothesis, our original analysis that we used when we were measuring it over a 60 days or a 90-day period. And that is typically associated with, in most of the literature on this, we'll put it at 5%, some will put it at 1%, some percent will put it at 10%. And what do we mean by that? 1%, 10%, or 2%, which represents the volume, the percent that's underneath this area as a percentage of our A sub O. That's a small probability out there that when we made the change over there, that the new raw material had no effect at all, but we mistakenly went ahead and said, yes, it does make an effect, and went ahead and changed the process anyways. That area, again, is called the alpha error, and sometimes the type 1 error. And it's typical the process of where we went ahead and made the switch of the process when actually it was just still one in the extreme tail of our original process that we were looking at. Now let's go to the other error. The other error is the beta error. And the beta error is the type 2 error, and it's typified by the blue. And notice where we have the blue at. We have the blue, which is actually starts right at the tail end of the alpha error. If I draw my vertical line up, it is the area, if this is 5%, then I would draw it up and I would draw the blue area as being the beta error. The beta error is the risk that, yes, in fact, the new raw material made a difference, but we didn't have enough evidence to support beyond reasonable doubt that the new raw material actually improved the process. This is the one that, think of these in terms of lost opportunities in the experimental world. That because of a certain amount of variability and other factors, which I'll talk to in 5 minutes here, that the beta error was so high that we actually couldn't find a difference when we switched the process around. Now, one other box associated, so let's back up and review that. We have the alpha error, and the alpha error is the typically 5% or 1% or 0.5% depending upon the process. That's the error that I went ahead and said that there was a difference when we put the new raw material on, but whoops, right? When in fact it really didn't make any difference. Those are the ones that you go ahead and make the change, and 3 months down the road you look at the economics of it and it basically didn't make any difference at all. You look at the scrap value, it didn't change at all. The yield output from this particular process didn't change. That it was all part of our original A sub O or null hypothesis or original data that we were looking at. That's the alpha error. The beta error is determined a lot by where you put where the alpha error is at. But the beta error is that error that basically said, yes, it would have made a change, but because a certain amount of data that we were looking at was underneath the original analysis, basically we couldn't find it, and we couldn't prove beyond reasonable doubt that there was a difference between the two. Now there is one other box that is critical in this whole process, and we're going to explain how to control that beta box off of there. Let's go back to the courtroom analogy for analysis. The courtroom analysis basically said is that he did it and found not guilty, and that was our beta error. He didn't add to it and was found guilty, and that's our alpha error. And then our box over here, this is where he did it and was found guilty. And that was where we put somebody on trial and for a particular crime, found evidence beyond reasonable doubt, and was found sufficient guilt for the process. In the experimental world, that particular box is in this area right here, typified by the green zone. The green zone has a specific name to it, and it is called power. And the power of your experiment is based upon where your beta error is at, in conjunction with how wide or how much area is underneath your alternative hypothesis. The greater the power you get, the more power you get in your experiment, the more likely you're going to find a change in your process that will improve it. The lower the power level, which is directly proportionate to how much beta error you've got in the process, will typically result in an experiment with very little findings off of it. So if you understand for the hypothesis theory, those three boxes, basically beta, alpha, and then the power, then those are the three critical factors of the hypothesis theory. Now let's go on to the next video, or next section right now, and we'll talk to, well, okay, how does that mean? Well, really, we want to improve the power coming off of here, and we got to do that by reducing the beta. So I want to go over several techniques to reducing the beta, and then when we're getting done, we'll explain how in a typical three-factor, two-level DOE, why this concept of the hypothesis theory comes into play. Okay, let's continue on. If we take a look at the hypothesis theory as we first put it onto the board, we have our H sub O, our null hypothesis, our alternative, our alpha error, our beta error, and our power. So what does all this mean? Well, let's take a look at it in theoretical concepts now. There's many ways that you can reduce that beta error. Now remember what we're trying to do here. We're going to try to reduce that blue zone, or the beta error. When we do that, automatically increase the power of the experiment. The power experiment is where you come up with your home runs, with your solid conclusions that don't have a lot of risk of failure once you put them in place. So if we take a look at the concept behind it, what we're trying to do is we're trying to eliminate or reduce the blue zone down so I can maximize the power coming out of it. So let's go over it. There's multiple ways of doing it, but let's go over two key ways of removing or eliminating or reducing the effect of the beta error. Number one, and one of the easiest ways to do it in the experimental process, is to move the experiments further apart. If this was an experiment that started off with an outcome of 45 on the yield, and this one was up at 65 on the yield, then instead of moving it for 45, move it up to 85. Now sometimes you can do that, sometimes you can't. But the base level concepts of DOE, for at least the initial effect, says move them out as further as possible without destroying the equipment. When you do that, then you reduce the beta error and you increase the power, as we've shown in the second graph here, where we have our alpha error. Beta error is essentially eliminated, and we have almost 100% power in our experiment, provided there's a factor associated with it. That's one way. Now that way can be done, and a lot of times can be done cheaply. A lot of times it can't be done though because of limitations on the equipment and facility. So there are other ways, and probably more effective way of reducing that beta error down to something more reasonable. And let's go to the bottom reason. The bottom reason is, the way in methodology, is the reduction in variation. So if I originally have my original process here, and now what I do is I reduce my variation. I have a small alpha error, and then I have, with the same distance going across, or the same split between the two, we now have a almost 100% power coming off of it, or elimination of the beta error. Now, how do you accomplish this one? What's the methodology of doing that one? Well, that one comes down to a lot of what you can do in the experiment as you design the experiments. You can reduce the variation down between your H sub O and your H sub A by doing such things as making sure the raw material stays consistent all the way through the experiment. There is no operator switching in and out from shift to shift to shift, that they're all consistently, and you try to do it over a 8-hour period, so it's consistency in personnel. Environment might be the other factor that is a cause of variability. If that's a particular case, then do it in the quickest area possible, maybe in the morning or maybe in the afternoon, but you don't want to do it over 2 to 3 days. There may be multiple different machines that you would be running the experimental process over. And if that's a particular case, then just pick one machine out and don't do it with the inherent variation that's going to come from doing it all across multiple different machines. Those are your typical things that are in your control as a designer to remove the variation out of the process so that you can see and so that you can find and improve the power by reducing the beta off the process. So that's one of the critical components. Now there's a few other ones. You can increase sample size, and that's one of the factors. You can also do some things with alpha, and alpha will have an effect on the beta of the beta error. I wouldn't recommend doing that, because if you increase the alpha error, which in turn reduces the beta, you're also reducing the probability that you're going to call it wrong when actually, or you're going to say that there was an effect when really there wasn't one. So the final two ones, increase sample size and playing around with your alpha error, are two ways of doing it, but I wouldn't highly recommend it. I would stick to increasing the separation and reducing the variation, and probably of the two, the reduction and the variation is a very, very powerful technique to remove, to increase your power experiment. So now let's go to an actual experiment and see how this comes into play and how this factor enters in. From the last video, if we were doing a three-factor, two-level, 8-run DOE, represented by the particular box plots. The first box is, and we're moving around the temperature, the pressure, and the concentration, and we're measuring the outcome of the process in terms of yield coming out of it. If we do the first one over here, and we move them all around in a specific pattern, if you looked at the prior videos, you would understand what we're talking about here, but each corner of the cube represents a particular combination of the three variables, the pressure, the temperature, and the concentration. If you look at this process, and you look at 45, 46, 48, 50, 51, 48, 52, and 50, determining what the factor or multiple factors are, or interactions are, based upon this particular output is very, very difficult, and you can do the mathematics behind it, and I've done the mathematics behind it, or you can just by looking at it determine that there is more noise than there is anything else, and try to prove beyond reasonable doubt that the pressure, temperature, or concentration, or a combination thereof, was a significant factor is nearly impossible. That basically all you have in this process is complete noise. This might be the particular output of a process that was done on the prior side with the excess variation, before the concept of reducing variation. This may be done with an experiment that was done over a multiple number of week period, with multiple number of operators, across multiple raw materials, across multiple machines, and with different environmental situations and situations coming off the experiment. Now let's go to the other side and go to that one and look at the particular effect of it, and look at it after we've done some things and we've reduced the time down to an 8-hour period, we've reduced it down to one operator, we've reduced it down to one gauge, we've reduced it down to one machine and one raw material. We now have 46, 45, 46, and 45, 50 and 50, and 54 and 55. We clearly now have staring at us is a interaction that is going on between our temperature and our pressure. Basically a classic two-way interaction between the two. Both of them need to be positive, and we will get a significant increase, most likely, in our yield coming out of the process. The point of this whole exercise, notice the difference between the two. We enter in the variability, the excess variability in the process. In this one, we tighten down the variability. And look how much easier it is to see. George Box used to address this in his lectures, where he said a well-run experiment would analyze itself. And that's basically what he was saying. He says if you're going to allow a lot of variation and variability into the process, it is going to be one that you're not going to be able to find any kind of a significant factors coming out of it. But a well-run experiment with variation reduction and with significant movements in the particular variables, and what will pop out of it is a significant interaction coming off of it. Keep that in mind when you're running the particular design of experiments or whatever experimental process you're going through. Variation is the killer of all DOEs. Reduction in variation is the gold mine. So keep the variation out of the process, most likely, and move them out as far as possible without destroying equipment, and see what happens when you do that, and most likely you'll find some significant factors coming out of it. This is the whole process, the whole concept behind the hypothesis theory and the application to design of experiments or the experimental world. I hope this helps in the understanding of this particular area. The next videos will explore further the design of experiments series, and we'll go into more detail on them. But this concept, base level concept, is critical to the whole implementation of the design of your design of experiments. Thank you.